Hi, my name is Enoch,
My name is Raymond.
My name's Adrian.
and today we'll be presenting about Chapter 15, Acids and Bases. So first off, we're going to start off with the definition of buffering capacity. Buffering capacity is the amount of protons or hydroxide ions the buffer can absorb without a significant change in pH. The formula for this is pH equals to pKa plus log A minus over HA, which is the ratio of the A minus and HA determine the pH of the buffer. This is known as the Henderson-Hasselbalch equation, and usually buffers rely on weak acids conjugate bases, or vice versa, weak base and conjugate acid. So first off, we're going to start off with the basic buffering problem. So we're going to calculate the change in pH that occurs when 0.01 mole gaseous HCl is added to 1 liter of each of the following solutions: solution A, solution B. And the Ka for this problem is 1.8 e to negative 5. So first we're going to use Henderson's Hasselbalch equation to find the pKa of the solution. And when following the steps throughout, we'll be allowed to find the pH later on. And finally, we can determine that the best choice of a weak acid is one that has a pKa of 4.0 or a Ka of 1 to e to negative 4. Now we're going to look at titrations and pH curves. We notice that at the equivalence point, there is going to be an equal amount of acid and base molarity added. Moreover, for a strong acid strong base reaction, water will generally be created and the equivalence point will reach a pH of 7, neutralizing one another. Moreover, for a strong acid weak base, the equivalence point will be slightly acidic, pH less than 7, and for a weak acid strong base, the equivalence point will be greater than 7. And if weak acids and weak bases are in comparison, refer to the Ka and Kb values. Moreover, we should memorize these simple acids: hydroionic acid, hydrobromic acid, hydrochloric acid, chlororic acid, chloric acid, sulfuric acid, and nitric acid. Meanwhile, looking at strong bases, there is sodium hydroxide, potassium hydroxide, lithium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, barium hydroxide, and strontium hydroxide.
Okay, so next we're going to talk about titration problem. So as you can see, there are different kinds of titration problems depending on the concentration of base that can be added to a solution. So let's talk about B first. First you have 50 milliliters of 0.2 molar HNO3 and 0.1 molar of NaOH. So for B, you're adding 10 milliliters of this 0.1 molar NaOH, and basically what you do is you take the concentration and the volume of HNO3 and NaOH and convert both to moles. Then you set up an ice chart and you see which one is the limiting, and once you do that, you subtract to find the amount of moles of H plus remaining, which you can finally use to find pH. Okay, so for acid-base indicators, basically mark the endpoint of a titration by changing color. Usually you'll look at charts like these to see what color it will change to. Choose an indicator for titration where the indicator endpoint and the titration equivalent point are equal to each other. Okay, so next we're going to talk about solubility, equilibria, and the solubility product. Solubility is basically, it's a measure of the dissolving of substance, and the product constant is represented by KSP. Solubility product is the equilibrium constant and has one value for a given solid at a given temp. So an example is CF2. CF2 is made by adding Ca2 plus and 2F minus. So KSP is found by multiplying the concentration of Ca2 plus and the concentration of F minus, but F minus is squared because the coefficient in front of the F minus in the original reaction is 2. And finally, the common ion effect is when an ion is added in a water solution in which that ion is common with the dissolving salt. So we will talk about a solubility equilibrium example. In this situation, we have copper bromide, which has a measured solubility of 2.0 times 10 to the negative 4 moles per liter at 25 degrees Celsius, and they ask you to calculate KSP value. So the reaction we see is copper bromide makes copper plus and bromide minus ion. Okay, so initially the solution has no Cu plus or Br minus, so the concentration is 0. But however, after reaction proceeds to the right, you would have 2.0 times 10 to the negative 4 mole per liter of copper and 2.0 times 10 to the negative 4 moles per liter of bromide ion. And once you plug into the KSP equation, you would get KSP is equal to 2.0 times 10 to the negative 4 squared. Okay, for next, we're going to talk about the precipitation and qualitative analysis. So Q, which is the ion product, is basically it uses this initial concentrations instead of equilibrium concentrations, which is K. K and Q are basically the same, except Q. You find Q and K the same way, except Q use initial and K use equilibrium concentrations. So once you find Q and K, if Q is greater than K, you shift to the left, which means you continue precipitation and reactants will continue to be used. However, if Q is less than K, you shift to the right, no precipitation occurs. And if Q is equal to K, then that means the reaction is already at equilibrium.
Okay, continue on with 15.7. Selective precipitation is when a region is used whose anion forms a precipitate with only specific metal ions. For example, Ba2 plus and Ag2 plus ions are in solution. If NaCl is added, AgCl precipitates because it's an insoluble chloride, while BaCl2 is still soluble. This method is used to separate metal ions. So group 1, insoluble chlorides, consist of Ag+, Hg2+, and Pb2+. Group 2, sulfides insoluble in acid solutions, include Hg2+, Cd2+, Bi3+, Cu2+, Sn4+. Group 3, sulfides insoluble in basic solutions are CO2+, Zn2+, Mn2+, Ni2+, and Fe2+. Group 4, insoluble carbonates, consist of Ba2+, Ca2+, and Mg2+. All in the alkaline earthline metal group. Group 5. Alkaline metals and ammonium ions all form soluble salts. So group 1A cations and NH4 form soluble salts. So here's a problem of a precipitation problem. A solution is prepared by mixing 150 milliliters of 0.01 molarity MgNO32 and 250 milliliters of 0.1 molarity NaF. Calculate the concentrations of Mg2 plus and F minus at equilibrium with solid MgF2 of KSB 6.4e to the negative 9. So the first step is to determine whether MgF2 forms. By doing so, we have to calculate the initial concentrations of Mg2 plus and F minus. We can see from these initial concentrations by using Q, the ion product, to see that Q is greater than KSP. Therefore, precipitation will be made because the reactants will have to be used up. Note that, based on the ice chart, F minus remains after the precipitation reaction goes to completion because Mg2 plus acts as a limiting reactant. Using MgF2, we can see how that if we redissolve this using the expression for KSP, we can find the concentrations of Mg2 plus and F minus due to the other table below. Initial concentration 0 and F minus 5.5 e to the negative 2. Next section is equilibria involving complex ions. A complex ion is a charged species consisting of a metal ion surrounded by a molecular ion which has a lone electron pair that can be donated to an empty orbital on the metal ion. This forms a covalent bond. Coordination number, the number of ligands attached to a metal ion. For example, COH2O62+. The CO resembles the metal ion while the H2O acts as a ligand, and this will have a coordination number of 6 because there are 6 H2Os. Complex ion problem. Calculate the concentrations of Ag+, AgS2O3- and AgS2O3-3- in a solution prepared by mixing 150 milliliters of 0.001 molarity AgNO3 with 200 milliliters of 5 molarity Na2S2O3. So first, you want to see that the K1 and K2 constants are relatively high. So the solution to this is you find that the initial concentration of Ag+ and S2O3-2-. Seeing that both of these are really large and that S2O3-2- is in both equations and that K are large, we can see that both formation reactions can be assumed to go to completion. And so according to the icebox below, you can see that Ag+ acts as a limiting reactant and S2O3-2- is in excess. Therefore, X is negligible for S2O3. By using the K values that you see, you can calculate the concentrations of AgS2O3 from K2. So K2 is equal to 3.9 e to the 4th. By taking products over reactants, we can see that the concentration of AgS2O3 is 3.8 to negative 9, and similarly you can do that to find Ag plus using K1. Thus, the assumption is valid that essentially all the original Ag plus is converted to AgS2O3 to 3 negative at equilibrium.